Hello everybody, let me present you the following poster. Investigation of the sintering of nickel, iron and magnesium powders alloy produced by mechanical milling that I prepared for the 33 International Materials Congress held in Cancun, Mexico in 2025. Let's have a look at the abstract. So powder metallurgy was a selected route to fabricate this nickel, iron and magnesium alloy. Initial powders of nickel, iron and magnesium were drill milled for 24 hours. Then the powders were uniaxially pressed at 500 megapascals to obtain an 8 mm diameter compact, which were then sintered at 1050 to 1100 degrees Celsius with a heating rate of 20 degrees Celsius per minute, all this in a vertical dilatometer under inert atmosphere. The sintering kinetics was estimated from the dilatometry data. Microstructure was determined by scanning electron microscopy and X-ray diffraction. Besides, X-ray patterns were also obtained in situ during the heating stage by using the same sintering conditions in a D8 diffractometer. The result indicates that milling time has a strong effect on the particle size distribution and the homogeneity of the crystalline structures of the powders. The estimated activation energy values were in the range of 97 to 190 kilojoule mole. Samples with a powder milling time of 24 hours presented higher relative densities, better distribution of the elements of the alloy, as well as the L21 and martensite phases, which will give the shape memory effect. It was also found that powders milled for 24 hours start at a lower temperature for the crystallization of the mill phases than the one milled, for example, at 12 hours. It was concluded that a larger milling time is favorable for better sintering and the more refined microstructures containing the L21 Heusler structure. Let's have a look at the experimental method. So we have here the initial powders of nickel, iron and these initial powders were weighted to obtain a stoichiometric ratio of nickel to iron magnesium for 50 grams of the alloy. Then the powders were put into a container with two 12 mm diameter alumina balls. The milling time was 24 hours. Here we can have a look at the machine, the high energy ball mill, SPEX 1000M. The following step was using a uniaxial compaction machine where we compacted our samples of with a diameter of 8 millimeters and a height of 12 millimeters. So we had them put in here in this uniaxial compaction at 500 megapascals. The following step was using a Bruker D8 diffractometer with high temperature chamber and control atmosphere, and we executed an in-situ X-ray from 473 to 1373 degrees Kelvin under an argon atmosphere, and the following step was using a vertical dilatometer, and we've done the sintering of the samples at a temperature of 1323 to 1373 kelvins during 1 hour and under argon atmosphere. Let's have a look at the results. So in the first images obtained with the electron microscopy, if we have a look we can see that the particle size distribution is lower than 10 micrometers. And also, most of all, you can see that irregular shaped particles are obtained. If we have a look at these graphics, when we have the actual strain function of the temperature in Kelvin, and have a look at these dilatometry curves, we can see that a strong dilatation is obtained by the formation of intermetallic compounds, and also a large shrinkage is obtained at the 1373 degrees Kelvin. On the second image, we can see that we have the strain rate function of the temperature also in Kelvin, and we have some in these curves. We can see that we have some peaks that indicate the formation of intermetallic compounds that were detected by dilatometry. And in here we can observe a similar behavior of both samples during densification. In these graphics we can observe these graphics obtained with energy specific X-ray spectroscopy, that after sintering at 1323 to 1373 degrees Kelvin, the L21 phase characteristic of the Heusler alloy is still present, as we can see. And in here we can have a look and see that during heating residual stresses are relieved, and we can also see that the formation of intermetallic phases were found between 723 to 1023 degrees Kelvin. And another observation was that after sintering, both alloys reached the L21 phase, characteristic of the Heusler alloy. So the formation of intermetallic compounds we can have it here, and also the Heusler alloy, it's reached after the milling process. All right. And if we have a look at another images obtained with the electron microscopy, we can see that residual porosity is noticed after sintering 1373 Kelvin. In here and in here we can see the porosity. And if we have a look at this electron microscopy image, we can observe some large lamellae are formed, and are mainly composed of nickel and iron. This large lamellae. All right. So in conclusion, it was concluded that NiFeMn alloy can be manufactured by mechanical milling, followed by solid-state sintering, below the melting point of the element, of course, which allow the formation and homogenization of the phases. Another conclusion was that the ferromagnetic shape memory effect could be present, and this is due to the formation of the L21 phase. It was also determined that intermetallic compounds are formed during the heating stage, which is also confirmed by the dilatometry tests. And the last conclusion was that additional work is needed to determine the magnetocaloric effect. Thank you all for your attention. Goodbye.